Hello Science Alliance, hello, I am Lara. This is Theory of Science. I am trained to teach physics up to A level, and now I just stream free live lessons into the internet. I know, it's working really well. It's working because pretty much, not all, but a lot of the people who watch are paying me, and I will explain to you how to pay me later if you want to. Most of you have probably already seen me before, because this is lesson 8 of the 4th module in our IGCSE physics course that we are doing. Hello Siobhan, using your mum's YouTube account. Good idea, hello. Right, we get to talk about Sankey diagrams. Sankey diagrams made the children in my classes when I taught in schools quite angry because it's a classic, why do we need to know this? Kids, you don't need to know this. Who needs to know anything? It's just interesting, isn't it? It's fun. Let's just do it. It comes up in the exams, and Sankey diagrams are basically a type of graph. I mean, if that doesn't get you excited, I don't know what is. I designed a PowerPoint. It's got colours on it. Here, look at this. Sankey diagrams use arrows to show energy transfers. We've been talking a lot about how energy gets shifted from one store to another, yeah? And we haven't really talked an awful lot about the numbers that you use to describe energy transfers. So this is a good way of doing that. There are a couple of rules that Sankey diagrams follow to display information. I don't think I'm going to even tell you any more than that. I think I'm just going to give you a minute to look at some and see what you notice. So here is a Sankey diagram showing the energy shifted by a petrol car. Okay, so if you imagine if you've just joined and you've never seen any lessons before, I'm really sorry, this isn't going to make any sense to you, but feel free to stay. But energy starts out in, we would say, the car's chemical store. So the petrol or diesel or whatever it is, plus the oxygen around the car, if it's a petrol car, is a chemical energy store. And then when you start the car, energy gets shifted from the car's chemical energy store to different stores. So here is an arrow going straight ahead saying energy transferred to kinetic store. And here's 2 arrows coming off the side saying energy transferred to surrounding air's thermal store, energy transferred to engine's thermal store. All right, so that's one Sankey diagram. What about this one? Energy shifted by an old-fashioned light bulb this time. Here's the energy from the chemical store of the light bulb. There's a big arrow going off to the side saying energy transferred by heating. And there's an arrow going straight ahead saying energy transferred by radiation, light. All right, so have a look at those two next to each other. What is going on there, eh? Like I say, there are a few rules that if you are lucky enough to have to draw a Sankey diagram, like for an IGCSE physics exam, there's a few rules that you have to obey to get the mark. I mean, they're not that complicated. I wonder if you can spot some of them. For example, why are some arrows coming off the side in these Sankey diagrams? Each Sankey diagram's got one arrow goes straight ahead and some arrows coming off the side. Should I just stop talking so you can actually think? Do you feel like you've got a couple of rules? I can see some comments going, that's good. Oh, yeah, excellent. Okay, brilliant. Yeah, people have got the idea here. Yeah, exactly. So on the petrol car, these 2 arrows are coming off the side, showing energy transferred by heating. In fact, it's the same with the light bulb. So yeah, the arrows coming off the side show the energy that has been wasted. That's right. A perfect car, what you want from a car is for the energy that is stored chemically to be shifted to the car's kinetic store, don't you? The movement store. That's the whole point, is you want a car to move. You don't want energy to be wasted heating up the engine or heating up the air. It just happens that way anyway. So yeah, that energy is wasted. Same with an old-fashioned light bulb, which I have here. What gorgeous things they are. They really got humans a long way. An old-fashioned light bulb like this, we've done about this in electricity, it's just got basically a really long, thin bit of wire all curled up in the middle of the bulb, which is just designed to get so hot that it starts to give off light. So obviously, it's what we call very inefficient. It wastes a lot of energy. And this Sankey diagram is a really nice way of just really quickly seeing that, isn't it? You can tell straight away that hardly, well, anyway, yes. The energy transferred by heating, that is wasted. That is not what you want. It's the energy transferred by radiation that is actually useful. Okay. So when I sort of touched on it already by accident. When we talk about how much energy something wastes, we are talking about how efficient it is. So I've kind of done a spoiler, I reckon. I think you can probably spot another rule about Sankey diagrams by looking at this one. Imagine your friend's got to draw a Sankey diagram for work. Perfectly believable scenario. Here's a Sankey diagram. They ask for your help. Can you look at this one and spot any other Sankey diagram rules? So here the energy input of whatever this machine is 100 joules. The arrow going straight ahead is saying that that's energy transferred by mechanical force to the movement of the turbine, which is 32 joules. And then there's two arrows coming off the side, one showing energy transferred by friction, that's 2 joules, and one showing energy transferred by heat via the exhaust pipe, and that's 66 joules. You spot another rule? I've sort of already told you, haven't I? You need to do some adding. Adding needs to happen. Have you spotted that the energy input is exactly the same as the energy output? So the 3 arrows, wherever they are, if you add them all together, you get the amount of energy going in. That makes sense, doesn't it? Oh, it makes perfect sense, because we've already talked about how, in loads of these lessons, we've talked about how energy cannot be created and it cannot be destroyed. It's got to go somewhere. So whether it's wasted or whether it's useful, all of that energy has got to add up to the energy that has gone in. Okay, let's draw a Sankey diagram. Now, not all of us have squared paper, not all of us have printers, so we're going to make really terrible squared paper all together. It's not even going to be square, it's going to be rectangular. What I need you to do is get a piece of A4 paper and fold it in half 3 times. And then you can just open it out again. We're going to use the creases as squared paper, so we all get the same result, so we all draw the same thing. Do you know what? I've been doing this for 5.5 years now, and I deliberately, very, very rarely use any equipment that you don't have. We just use household objects, don't we? I know I'm biased, I honestly think it's better. I think it really helps understanding. I think even squared paper, it's not something that you sort of come across in your everyday life, is it? So straight away, it just, for me, it makes it all a little bit more intimidating and a little bit weird. Whereas using paper that has been creased up, I don't know, my brain enjoys it. I hope your brain does too. So if you folded a piece of A4 paper in half 3 times, you will end up, hopefully, with your piece of paper split into 8. So whichever direction you've done it in, you need to do it again in the opposite direction. So we end up with, not squares, rectangles, which, I mean, it's not perfect for our needs, but it'll do. So yeah, we're talking about energy efficiency, how much energy machines waste. It's kind of the invention of machines that got humans thinking about energy in the first place. The Institute of Physics are very big on this idea that you shouldn't even really bother talking about energy without talking about numbers. It's like trying to talk about money without talking about numbers. It's just pointless, isn't it? You've got some money, I've got some money. It doesn't mean anything unless we put numbers to it. So this is a really nice way, I think, of being able to actually talk about the numbers in a way that also sort of looks good. Here we go. I think I've done all of my creases. Yeah. So the energy in always equals the energy out. That's one of the rules. And what that means is, because this is a graph, is that right? Yeah, that's enough. What that means is you've got to draw your arrows proportionally. So if the energy going in is six rectangles, then the energy coming out, all the arrows that you draw, has to also equal 6 rectangles. I'll show you the rules first of all. Here we go. So the rules for Sankey diagrams, how to get full marks in an exam if you're drawing a Sankey diagram. The energy in has got to equal the energy out, so you might have to draw it to scale like we're about to do, or maybe you could label it. Yeah, so the width of the arrows is proportional to the amount of energy. So the width of the arrows shows you the amount of energy, just like on a bar graph, right? Or if you imagine a pie chart, the size of the pie shows you how much stuff is represented. It's the same sort of thing. So big arrow means a lot of stuff, little arrow means not very much stuff. And the useful energy comes straight ahead, and the wasted energy comes off the side, which makes sense, right? It's just easier to read. So straight away, if I tell you that this is a Sankey diagram of a light bulb, you can see without thinking too much about it, there's not very much useful energy in the process of having an electric light bulb running, and lots of energy is wasted. You can just tell straight away. Okay, so hopefully you've got your bit of paper now. You folded a piece of paper in half 3 times, so you've got some lines, and then you've done it the other way around. You've got some other lines. This is our squared paper, so in a sec I'm going to ask you to draw a Sankey diagram. I'm just going to give you like a quick example on the board that I definitely didn't knock together just before this lesson, and it's why I was late. So if I said to you, like, draw a Sankey diagram of a machine with an energy input of 4 joules, hopefully that would be fairly straightforward because you've got 8 squares on your bit of paper. I mean, usually when you're drawing graphs, you would be told use as much of the paper as possible. I'm not going to make my machine like 8 squares wide. I'll just make it 4 joules wide, so we've got room for the my graph 4 joules wide, so we've got room for the arrows coming off the side. So a machine with an energy input of 4 joules, I'm going to draw a line showing, like, covering 4 squares, right? 1 joule per square. Nice. If it was a Sankey diagram of a machine which wasted 2 joules, what are you going to do? Okay, I'll say 1 rectangle equals 1 joule. So I'll start drawing my lines. It wastes 2 joules, so I've got to draw an arrow coming off the side because wasted energy comes off the side. And it's got to be 2 rectangles wide, yeah? You okay with that? So that's good. If 2 joules is wasted, no energy is ever created or destroyed, so 2 joules must be useful. So I've got to draw another arrow coming off the front, like straight ahead, showing the useful energy. And then you've just got to kind of join it all back up together. Phew. Is that okay? So this would be, obviously I would have to label it, but this would be a good Sankey diagram for a machine with an energy input of 4 joules. 1, 2, 3, 4, wastes 2, so therefore 2 is useful. 2 rectangles there, 2 rectangles there, adds up to the energy that goes in. Yeah, brilliant, okay. So you're going to do a slightly more complicated one because it's not going to be a nice little number like 4. In fact, it's going to be 100. So what are you going to do? How many joules is 1 square going to equal? I'll just do it, I think, behind you, and then I'll show you mine. I want you to fuse a few neurons here. If you just sit in front of this for the 3 minutes in which we're doing it going, I don't know, I don't get it, this is so confusing. I know it sounds awful, but that's actually kind of fine because there's loads of examples of Sankey diagrams online. There's not that many opportunities to get Sankey diagrams wrong online. I'm giving you the opportunity, chums. I know, you're so lucky. What I want you to do, please, is using your terrible square paper, which is actually rectangles, can you try and draw and fully label a Sankey diagram for an LED bulb? That's a good bulb that we have now that is much more efficient, that uses 100 joules of energy, transfers 25 joules to the air by heating, and the rest by light. So it's 100 joules of energy is the input, 25 joules gets shifted to the air by heating, and the rest of it is shifted by the light pathway. Questions which my children in my classroom would have asked me years ago? No, you don't have to use a ruler, I suppose. I can't see you. I will be using the edge of a CD case. Yeah, you do have to put the numbers on. That's what fully label means. Please do that. Make sure you make the width of the arrows proportional, please, as well. And it doesn't matter which side the wasted energy comes off. The wasted energy could come off the top or the bottom. As long as it's not coming off straight ahead, then you're fine. Okay, shall I do this as well? Yeah, there's some good comments going on, which I guess you can read or not read. Depends if you want any clues. Are you all okay with, if you need to show 100 joules and you've only got, what, like 4, 5, 6 squares? You've got to show 25 joules being wasted. So what would be a sensible amount of joules to say each square? I'll give you a couple of seconds and then I'll tell you, because someone in the comments has got it. Yeah, so well done, person in the comments who said you would use one square to be, or one rectangle to be 25 joules. I agree, yeah. So I'm going to draw a line like that, 4 rectangles wide, and say that each one of those is 25 joules, yeah. I've sort of done a little key. I don't know if that would get me a mark at GCSE, but one rectangle is 25 joules. So 25, 50, 75, so I've got an arrow that is 100 joules wide. All right, carry on, as you were. Oof, how are you getting on? Do you want to mark mine with me? You've got to be so careful of your language here, haven't you? Talking about things getting shifted. You've got to be really clear on what your energy stores are and what your energy pathways are. I'll give you, I'll just sip a little bit of coffee and then I'll show you what I've done. If you're bored, you can always like and subscribe. All right, let's have a look at mine. See if you reckon I've got 4 marks. Here we go. So I've done the energy input. I mean, you don't have to do the same proportions as me. I just think this is the easiest way to have done it. So the energy wasted, you have to spot that if it's a light bulb and 25 joules is heating the air, that is not a useful thing to do. So 25 joules was getting wasted, which I've done. So the energy in is always going to equal the energy out. So if 25 joules is wasted, 75 joules must be useful because 100 joules went in. So are you all right with that? Do you think I've got away with it? So I've got 1, 2, 3, 4 rectangles all together sort of coming off. And I've got 4 rectangles going in. So that's good. That would be like 1 mark because all my arrows are proportional. My wasted energy is coming off the side. That's good as well. And yeah, it's all labelled. I think that's all right. Here's one that I did a couple of years ago when we did this lesson. Yeah. Oh, I've labelled that. This was quite a good time to say this actually. Someone was getting confused yesterday on Facebook and talking about light as an energy store. Light is not an energy store. It's really confusing. Do you remember how we've talked about stores and we've talked about pathways as well? So what we're talking about at the moment is pathways. Like if my body is a chemical energy store and I lift this up, then I'm shifting energy to the box's gravitational potential energy store. Is that okay? But the pathway, like how it gets transferred, is by force, like me pushing against gravity, right? So with this one, we're talking about the pathways. So energy from a light bulb, we would say the energy gets shifted via the light pathway. Is that okay? When you turn on a torch, the sort of ultimate result is that the energy from the torch's chemical store heats up the air, I suppose, like goes into the shifts to the thermal store of the air. But the pathway is radiation. So it would be like heating by particles, but radiation. So it's light. Let's move on. Okay, I've got a little quiz for you here. Is it a quiz? It's just one question. Does that count? A machine wastes 9,000 joules of energy. Is it A, very efficient, B, very inefficient, C, can't say? If a machine wastes 9,000 joules of energy, is it A, very efficient, B, very inefficient, or C, can't say? Well, you might be saying that 9,000 joules of energy sounds like a lot, so it's really inefficient. But, though, can we really say? Like, if its energy input is 9,001 joules, then yes, it is wasting a huge proportion of energy. Very wasteful, very inefficient machine. But if its energy input is a billion smillion joules and it's only wasting 9,000 joules, like, that's pretty efficient actually, isn't it? So sorry to be an annoying trickster, but we actually need a little bit more information. If a machine wastes 99% of its energy input, is it A, very efficient, B, very inefficient, or C, cannot say, if it wastes 99% of its energy input? Oh, Rocklyn's here, and someone is agreeing with them. Oh, well done, Rocklyn. Yeah, exactly. Oh, nice. So Rocklyn in the comments is saying, we can't tell until we have the energy input. Yes. So in a way of showing the energy input is to turn it into a percentage. If a machine is wasting 99% of its energy, then we can definitely say that that is very inefficient. With percentages, we know for sure. And because what percentage actually is what Rocklyn is doing. It's showing us the energy output compared to the energy input. So the equation for how efficient a machine is the total energy output divided by the total energy input, and then times 100 to make it a percentage. Are you okay with that? If I'm doing, sorry, just knocked over my little bit of Lego, which is propping you up. Whenever I'm doing percentages, I always find it easier to think of dividing as being like out of. So if you wanted to know, wrong blue pen, I don't need to refill that. If you wanted to know the percentage like of what like 5 out of 10 was, then if a machine has an input of 10 joules and it's using usefully 5 joules of that, you would say, okay, 5 joules is being useful out of 10. I don't know, it just helps me, so maybe it'll help you too, it's worth saying. So 5 joules out of 10 joules are useful, so that would give you, what's 5 divided by 10? 0.5, and then you times it by 100 to turn it into a percentage. So you remember how to times things by 100. If your decimal point is here, if you move it forward 1, you times it by 10, so 0.5 times 10 is 5, and if you times it by 100, you move it forward twice, so times by 10, times by 100, so you get 50. You just basically move your decimal point to a different place. I think I did that the wrong way around, didn't I? Because I'm writing backwards. But anyway, it's 50%. A quick note that when you divide joules by joules, just like when you divide 2 by 2, you get 1, 10 divided by 10 is 1, a billion divided by a billion is 1, a joule divided by a joule, the joules just cancel out. So you don't have any joules in your answer if you've done like 10 joules divided by 20 joules or whatever. Okay, shall I just stop talking and give you some questions? Is that okay? Here we go. So for some of you, this will be quite a straightforward equation, but some of you won't have done very much maths before. So the useful energy output is the amount of useful energy that goes in. So in this case, it would be 32 joules. And then that's out of however much energy you put in, which in this case would be 100 joules. So this one would be dead easy because you're doing 32 divided by 100, and then you're timesing it by 100. So the answer is just 32%. I'm going to give you some questions. They're not actually that complicated. I've really not tried, I've not put any like trick questions in here. It just looks like loads of words on the screen. I'm really sorry. If you have the printout in front of you, hopefully it doesn't look that intimidating because I've left you little gaps and things. But for the people who don't have the printouts, I've got to put all the questions on the board for them. So sorry if this looks a bit like, I don't know, mind tricksy, but I'll read them through. Just take them one at a time. Question number 1, a motor uses 600 joules of energy to do 150 joules of useful work. What's its efficiency? So a motor has an input of 600 joules of energy, but it's only doing 150 joules of useful work. So how efficient is it? You might be able to do that without a calculator if you like numbers. Question number 2, or you can use the equation. There's no points for not using a calculator in physics exams. Here's a little Sankey diagram. Fill in the missing value on this Sankey diagram for a light bulb. So you've got the energy input is 260 joules. The energy transferred by light is 140 joules. And then you've got an arrow coming off the side saying energy transferred by heat, and there is a gap. So can you tell me what that gap is? How much energy is getting transferred by heat? And then once you've done that, can you calculate how efficient the bulb is? So you need to know what a bit of this energy is the useful energy output, and do that divided by the total energy input and then times it by 100. Number 3, a plug-in, close to my heart, I didn't realise this. A plug-in phone charger, so just a normal phone charger basically, where you actually stick it into the phone, uses 20 joules of energy. 12 joules is shifted to the phone's battery, and 8 joules heats up the air around the charger. How efficient is the charger? Next question, a wireless phone charger uses 7 joules of energy, and 6.3 joules heats up the air around it, and the rest charges the battery. How much energy is shifted to the battery? And so, which charger is more efficient? And if you've got through all that, then just a sort of little brain exercise quiz for you. The glowing filament in a toaster, the red coily bit in the middle that gets really hot, receives energy electrically. 100% of this is shifted to the filament's thermal energy store. So is the toaster 100% efficient? Explain your answer. I'm quite pleased with that last one. What you can hear is me clearing Lego out of the way. I'm just wondering how I can make tomorrow's Lego story about witches better than it was today. I think I can, you know. Oh yeah, I definitely can, yeah. How are you getting on? It's quite useful actually having a few comments on YouTube to let me know when you've finished. Oh, here we go. 5 question mark. Okay. I'll give you just a few more seconds to try and clear up those question marks, and then we'll crack on. Yeah, I forgot I made a little Lego church. Coloured in the stained glass windows and everything. Crack that out tomorrow. Okay, you lot, should we go through it? It doesn't matter if you haven't finished, as long as you've done the first couple. So, a motor uses 600 joules of energy to do 150 joules of work. What is its efficiency? Well, it's 150 joules is useful out of 600 joules. So it's 150 joules divided by 600 joules, which equals 0.25, and then you times that by 100 and you get 25%, which you might have spotted anyway. You might have spotted that 150 times 4 is 600, so a quarter of the energy is being useful. Fill in the missing value on this Sankey diagram. Okay, well, energy can't be created or destroyed, so if 260 joules goes in and 140 joules is used usefully, then whatever's left is going to be transferred by light. So it was just the energy in minus 140 joules, which equals 120 joules. So now you know how much energy is wasted. Let's calculate how efficient the bulb is. So it's the useful energy, 140, divided by 260, because that's the energy in, and then times it by 100, so it's 54%. This diagram was awful, wasn't it? That didn't give you any clues at all. But hopefully, if you checked your answer, which you always should do in an exam, you would sort of spot that 54% is about right. Because the energy going in is 260, half of 260 is 130. So if this thing was 50% efficient, you'd expect 130 joules to be transferred by light. And it's just over 130, so just over 50%. Sounds good to me. Moving on. Oops. A plug-in phone charge uses 20 joules of energy. 12 joules is shifted to the phone's battery. 8 joules heats up the air. So it's the 12 joules that is useful. So it's 12 joules divided by 20 joules times 100, which is 60%. A wireless phone charger, the energy being shifted to the battery is 7 minus 6.3. 6.3 joules out of 7 joules are getting wasted. So it's 0.7 joules that are useful. So it's 0.7 joules out of 7 joules times 100. Gives you an efficiency of only 10%. I did not know how inefficient these things are. I am the kind of person that drops my phone on a regular basis and eventually destroyed my phone to the point where the charging port didn't work and I couldn't plug it in. So I did get one of these things. I was so happy to find that you could just put it on a wireless charging station and it would heat up by induction like that. But very inefficient. So I eventually did replace my phone so that I can stick a charger in it. Well, it died. It won't surprise you at all to hear that it died. Anyway, yes, so the answer was, which phone charger is more efficient? It's the one in question 3, isn't it? The one where 60% of the energy is useful. And finally, last question. Okay, so you've got a toaster. Let's have a think about this. So you've got a toaster. It's powered by electricity, right? Coming from the power station or whatever that's attached to your house. So energy goes in. 100% of the energy input of the toaster is shifted to the filament's thermal energy store, the red glowing bit inside the toaster. So is it 100% efficient? No, it's not, right? Why not? So I'm just reading the comments and laughing. It's not, because not 100% of that energy in the filament's thermal energy store is shifted to the thermal energy store of the toast, is it? Some of that energy heats up the toast, but quite a lot of that energy will just be heating up the air around the toaster. So be very careful. There really isn't, I feel like I can say this with confidence, there is no such thing as a 100% efficient machine, because friction will always exist. Bits are always going to get hot, that you don't want to get hot. Okay, and on that note, on that deeply scientific note, that was the end of our last IGCSE lesson before half term, which if you watch on catch up, probably doesn't actually mean that much to you. If you're watching live or you're watching it soon after I teach this lesson, then I've got a week off now for planning, and then after that we'll do more energy lessons, but we'll sort of take a slightly different angle. So we'll start looking at power stations, how power stations work and generate electricity, and all the different ways that you can generate electricity. So it's nice. I'm looking forward to that one because it kind of relates to real life, possibly a little bit more than Sankey diagrams. This is, person asking me in the comments, this is IGCSE physics. So physics is a type of science. You can also do IGCSE biology or IGCSE chemistry, or you can do an IGCSE that like mixes them all together. So this is, we're not going to do anything about like reproduction or mushrooms. This is physics, like waves and electricity and energy and forces and all that stuff. Okay, I'm going to go over to my Facebook page and see if anyone's left me any comments, because as you know, whenever I'm live on YouTube, I always have a post on the top of my Facebook page saying that you can comment there if you like. Rocklin might have commented. I don't know, is Bastian around? Maybe Jacob's here? Let's have a look. There's a lot of you commenting actually on the video today, which is nice. Ah, Hannah and Freya! Hannah, who's making cornflake tart. Oh, is that one of my favourite foods? I'm just like skidding right back to school where it was pastry and then jam and then sticky cornflakes on the top. I'm used to getting it with custard. Is that what you're making? Or are you making like cornflake crisp? Whatever it is, I cannot think of a cornflake related food that isn't deeply pleasing me, Hannah. So well done. Well done for putting cornflake food into the universe. And also hello Freya, who is actually doing this lesson. Hi Freya. Hiya. Oh, hello Edmund. This is Edmund's diagram. He says it makes more sense to him to have it this way up, with the bottom of the diagram as a straight line pointing towards where the energy is being used. All right. And the energy wasted coming off the top, as this gives a clear visual representation of where all the energy goes. He doesn't like the versions where the arrows are put differently. Oh yeah, I see what you mean. All right, let's have a look. Hello Jacob, hello. At the beginning, I read Sankey diagrams. That's a better word for them. All right, let's have a look at Edmund's. Oh yeah, okay. Oh yeah. Oh yeah, that works, doesn't it? Sorry, Edmund, but it is really handy to be able to actually look at somebody's. What do we think? Do we approve of Edmund's drawing? So you can see 1, 2, 3, 4. Yeah, you've done the same as me, haven't you? 4 rectangles. And then that is 1, 2, 3 rectangles wide. Is that 1 rectangle? Yeah, I think it's actually. Yeah, very nice. Very nice apostrophe there. Yeah, beautiful. Very good. I heartily approve. Yeah, we're all approving. Thanks, Edmund, for giving us that chance to approve. Okay, you lot. Well, if this is the last thing of mine that you see, then thanks for joining me. Have a really lovely, like, half-term / just break from me. And I'll see you in, what is it, like a fortnight's time? Or I'll see you tomorrow if you like the YouTube things that I do. I might see you tomorrow at 9 AM for the all ages lesson about the oceans, or I might see you at 10:30 for the Lego story show about witches. So whenever I see you, thank you so much for joining me. Thank you so much for paying me £5 a month for these, for doing all this work so that I can actually do my job. You know that I send you nice things, right? Of course you do. You know this. Very IGCSE related stuff. I send you a magazine about time and mould, depending on how much you pay me, and some diffraction glasses as well. So if you haven't signed up and you fancy a little welcome pack to sort of entertain you in the holidays, then please do. Bye, Rocklin. See you soon. Thank you for all the comments. It really does help, actually. It's nice having comments on YouTube. Oh, splendid. Okay, well, I will see you tomorrow morning then. Bye, everyone. Thanks for coming. Bye.